Hi folks, this is Linear Algebra Take Home 1. We're reminded of the definition of a diagonal matrix. So Dij is called a diagonal matrix if Dij is 0 if I and j are different. So that means that we have these entries along the magnitude diagonal here, and zeros everywhere else. That's what a diagonal matrix looks like. So number one, we're asked to prove if you take the diagonal matrix and square it, the result is just squaring each of the individual entries, which is somewhat unusual for matrix multiplication. But you can visualize that. If you take this and multiply it by itself, you can start to see why this would actually be the case. We're asked to use the definition of matrix multiplication to prove that, so that's what we'll do. We start off with d squared, and by definition that means I'm taking d times itself. I'm going to write this entry-wise, Dij times Dij, and now I'm going to apply the definition of matrix multiplication. So to get the ij entry of the product, you take the ith row of the first factor times the jth row of the second. So this is going to be dik dkj. So that's what's going to be in the ij entry. And so the key to the proof is now looking at what this sum is going to be in the various cases. So what do I know about this matrix? It's diagonal. So I know it has this property. Whenever the subscripts are different, the entry is going to be 0. So if I look here, if I and k are different, dik will be 0, which is going to zero out that term. And the same thing is true for the dkj. So I'm going to write that down. So I'm going to just note here, if I and k are different, dik is 0, and so is dik times dkj. If k and j are different, then dkj is 0, and so is dik dkj. So once again, I'm just applying the definition of diagonal matrix. So what's the only chance I'm going to have for getting a non-zero term out of this sum? Well, I and k are going to have to be the same, and k and j are going to have to be the same. So in particular, I and j are going to have to be the same. So if I equals k equals j, then dik dkj, well, I, j, and k are all the same. That's then dii times dii, which is dii squared. So that's the three different cases here for what these terms are going to look like. Okay, so what does all this mean for this summation? Well, this summation is going to be one of two things. If the I and the j are different, then the dik dkj, one of them is always going to be 0. Because even if the k matches with the I, the k at that point won't be matching with the j, and vice versa. So this is going to be 0 if I and j are different. And if I and j are the same, well, that's this scenario, and that just gives me dii squared. And this is what I need then to conclude the answer for the proof. Because 0 I can write, if I want, as 0 squared. And so I can rewrite this as dij squared if I and j are different. Why? Because when I and j are different, dij is 0. And I could write this too as dij squared because when I equals j, dij, when I equals j, dij is the same as dii. Hence, in all cases, the summation k equal 1 to n dik dkj is dij squared, and that's what I needed to show. Now number 2, give an example of a non-diagonal square matrix where a squared is not the square of its entries. So let's just pick a generic 2 by 2, say 1, 2, 3, 4. So that's a 2 by 2 matrix, and let's compute a squared. That's a times a, which is 1, 2, 3, 4. 1, 2, 3, 4. I take the row times the column. 1 times 1 is 1. 2 times 3 is 6. 1 plus 6 is 7. Row times column. 1 times 2 is 2. 2 times 4 is 8. Add those together, you get 10. Row times column. 3 plus 12 is 15. 6 plus 16 is 22. And I can compare this now. I mean, certainly, if I square each of these entries, I'm not going to get anywhere near this matrix here. So that just goes to show that we really need a diagonal matrix to make this magic work. That'll do it for take home 1.